66 million years ago, the last full day of the dinosaurs began like any other. Rivers still moved through the Hell Creek floodplains. Fish still fed in channels connected to the retreating Western Interior Seaway. Triceratops still crossed low ground under conifers and flowering trees. There is no evidence that any animal on Earth had the slightest warning that before the next day was over, the Mesozoic world would be broken. The question is not whether an asteroid hit. That part is settled. Walter Alvarez and his colleagues found the iridium-rich boundary clay in 1980. Shocked quartz turned up around the world. Drilling and seismic imaging later revealed the buried Chicxulub crater under the Yucatan. The question is how much of the final day we can actually reconstruct. And the answer is more than most people realize, though not in the way disaster movies usually tell it. The rocks preserve an impact. The boundary clay preserves fallout. Crater cores preserve the violence at ground zero. A site in North Dakota called Tanis may preserve animals caught in the first hour, though some details there remain debated. Climate models preserve what happened after the sky filled with dust, soot, and sulfate aerosols. Put those lines of evidence together, and a grim picture emerges. The last 24 hours before Chicxulub were ordinary almost to the final minute. Then, the planet changed faster than most large animals could survive. Start in western North America, late Maastrichtian, about 66 million years ago. This was not a dying wasteland. It was a working ecosystem of river channels, swamps, floodplains, forests, insects, fish, crocodilians, turtles, birds, mammals, and the last great non-avian dinosaurs. Whether dinosaur diversity had already begun to thin in some regions is still debated. What matters for this story is simpler. Life was still running on normal ecological time. In what is now North Dakota, Montana, South Dakota, and Wyoming, the Hell Creek world held Triceratops, Edmontosaurus, Tyrannosaurus, smaller theropods, amphibians, freshwater fish, and dense plant life. Far to the south, near the Yucatan platform, shallow seas covered carbonate and evaporite-rich sediments. Those buried rocks would matter once the asteroid arrived. This is the hardest part of the story to imagine, because nothing in the sky would have looked unusual to a dinosaur on that final morning. No smoke on the horizon, no long warning siren from geology, no slow buildup a living creature could understand. Deep time often feels gradual. This event was not. At some point on that final day, a carbonaceous asteroid, roughly 10 to 15 kilometers across, struck the northern Yucatan Peninsula at an oblique angle. Joanna Morgan and colleagues, summarizing decades of Chicxulub research, placed the crater at about 200 kilometers wide and the impact energy at about 10 to the 23 joules. That number is so large it stops being intuitive. What matters is its effect. The asteroid hit carbonate and evaporite-rich rocks, plus seawater and deeper silicate basement. In a geological instant, target rock and projectile material were vaporized, melted, crushed, and thrown upward at extreme speed. Several thousand gigatons of material were launched into a fast-moving cloud. Some ejecta left the impact site faster than 5 kilometers per second. The crater itself did not form as a clean bowl. It collapsed, rebounded, and reorganized into the giant buried structure geophysicists have now imaged in detail. Near ground zero, the destruction was immediate. Seismic shock, thermal radiation, blast effects, ejecta fall, ocean displacement, and collapsing crust all arrived in a chain too fast for animal behavior to matter. But most of the world was not at ground zero. That is where the timeline becomes more complicated and more interesting. Within minutes, the rest of the continent began to feel the impact through the Earth itself. The Chicxulub collision likely generated one of the largest earthquakes in the history of complex life, commonly estimated in the magnitude 10 to 11 range. Strong seismic waves radiated across North America long before any direct tsunami from the Gulf could have reached inland river systems. That timing matters because one of the most famous lines of evidence for the first hour comes from Tanis, a K-Pg boundary site in North Dakota, described by Robert DePalma and colleagues in 2019. There, a violent surge deposit contains freshwater fish packed together with impact ejecta, including tiny glassy spherules lodged in their gills. If that interpretation is right, those fish were alive while ejecta was still falling out of the sky. That does not mean every detail of Tanis is settled. A 2024 study led by LeVeque tested the surge mechanics and concluded that a direct tsunami from Chicxulub could not have reached Tanis within the 1 to 2 hour depositional window inferred for the site. It would have taken much longer, more than 10 hours. Their modeling instead favors a surge triggered by seismic shaking in the Western Interior Seaway, something closer to a giant seiche or seismically coupled water surge. That distinction matters because it sharpens the physics. If Tanis records the first hour, the fish were not killed by a wall of water racing all the way from Yucatan. They were likely caught in inland surges triggered by the earthquake and basin-wide water motion, while impact debris was still arriving from above. While seismic waves shook the continent, the atmosphere was beginning its own phase of violence. Ejected debris arced around the planet. Some particles re-entered the atmosphere and dumped heat back into it. Fine material spread rapidly. Morgan's 2022 review notes that dust, soot, and sulfate aerosols were transported around the Earth within hours. This is where older popular versions of the story often become too simple. You will sometimes hear that the entire planet caught fire at once. The real evidence points to widespread fire activity, but not necessarily one single synchronized firestorm in every forest on Earth. Some regions likely burned quickly. Others may have been devastated more by darkness, cooling, and food web collapse than by immediate flame. Even so, the thermal pulse and returning ejecta would have turned the sky into a threat almost everywhere. For animals exposed on open ground, the first dangerous signal may not have been a sound at all. It may have been what the sky started dropping. At Tanis, if the site is being read correctly, some fish were literally breathing that fallout. That detail is so vivid because it reduces a planetary catastrophe to one body in one river channel. The world-ending mechanism was global. The experience was local, physical, and immediate. The impact itself did not need to burn every dinosaur alive to end the age of dinosaurs. It only needed to break the systems that kept large animals fed. That is what the atmosphere did next. For years, sulfur aerosols were treated as one of the main climate weapons of Chicxulub. The target rocks beneath Yucatan were rich in sulfur-bearing evaporites, so the logic made sense. But the picture has changed. In 2025, Katarina Rodishkina and colleagues estimated an average sulfur release of 67 plus or minus 39 gigatons, around 5 times lower than many older numerical estimates. Their conclusion was careful. Sulfur still mattered, but perhaps less than the classic models assumed. That change does not weaken the extinction case. In some ways, it strengthens it by pointing to another agent that may have been undercounted. In 2023, Sem Burke-Sennell and colleagues modeled the effect of fine silicate dust and argued that Chicxulub launched much more micrometer-scale dust than many earlier reconstructions allowed. Their simulations suggested that this dust could have remained in the atmosphere for about 15 years, driven average global surface temperatures down by as much as 15 degrees Celsius, and shut down photosynthetically active sunlight for almost 2 years.
That is the line that matters most for the dinosaurs far from Yucatan. Once sunlight fails, plants fail. Once plants fail, herbivores fail. Once herbivores fail, top predators fail after them. Large-bodied animals built for stable food supplies do not handle sudden darkness well. So when people ask what killed the dinosaurs, the most honest short answer is this. For many of them, it was not the first flash, it was the collapse that followed.
A dinosaur standing in what is now Mexico near the impact zone had no future at all. A dinosaur on the North American interior had minutes to perhaps an hour before the environment around it became chaotic. A dinosaur on another continent might not have faced lethal heat or water on the first day, but it still entered a world where the sky was closing down and the food chain was about to come apart. This is the uncomfortable part of the reconstruction. The title sounds like a single day. The extinction was a cascade. Some organisms died within minutes, some within hours, some within days, weeks, or longer as ecosystems failed. There was no clean, universal moment when every non-avian dinosaur on Earth disappeared at once. That is also why a few lineages made it through. Small body size helped. Freshwater systems may have buffered the worst immediate disruptions in some places. Generalist diets helped. Seed eating may have mattered. Burrowing and sheltering behavior mattered. Crocodilians, turtles, some birds, and mammals were not invincible. They were simply better matched to the ruined world that followed. Large terrestrial dinosaurs were not. Some parts of this story sit on very firm ground. Chicxulub happened. The crater exists. The iridium anomaly is global. Shocked quartz and ejecta link the boundary to impact. The mass extinction followed. Other details remain active science. Tanis is one of them. The deposit is real and the impact link is strong. But exactly how to interpret every signal from the site is still argued over. One 2021 paper on the seasonal timing of the impact, also based on Tanis material, currently carries an editor's note from the journal warning that the reliability of the data is in question. That does not erase every observation from Tanis, but it does mean careful scripts should not present the boreal spring timing as settled fact. The wildfire story also needs restraint. There is strong evidence for severe post-impact burning and soot in the atmosphere. That does not mean every landscape ignited at the same moment. The climate story is still being refined, too. Older models leaned heavily on sulfur aerosols. Newer work gives fine silicate dust a larger role. Those are updates in mechanism, not doubts about whether the event was catastrophic. Science often gets more interesting when the details sharpen. Chicxulub is a good example. The broad outline has been settled for decades. The exact kill chain is still being resolved layer by layer. So what did the last 24 hours before the asteroid hit actually look like? They looked normal until they did not. Rivers flowed, fish fed, insects moved through warm air. Dinosaurs crossed floodplains with no sign that a space rock was already on course to end their world.
Then Chicxulub struck Yucatan, excavated a crater about 200 kilometers wide, launched dust, soot, and sulfur-bearing material into the atmosphere, shook continents, drove violent water surges deep inland, and dimmed the sunlight that the global food web depended on. The first hour was terror and physical shock. The next hours brought fallout, darkness, and fire in at least some regions. The next months and years brought cold, hunger, and ecological collapse. That is why the last day of the dinosaurs is both simpler and harsher than the popular version. There was no warning, there was no adaptation window, there was only a normal morning followed by a broken planet. If you want more prehistoric documentaries built from the actual science, subscribe. And if there is another extinction, fossil site, or final day reconstruction you want next, leave it below.